Good morning. It's whatever day it is, Tuesday. And does anyone have any questions about homework? I don't know if anyone's tried any of the new homework problems yet or not. Those are always fair game for asking questions about. Let's see. Yesterday, it took me, well, after I finish recording this class, at the end of it, I have to first convert the Zoom meeting into an MP4 on my computer, and the software automatically does that. The Zoom software does. And let's see, it's been 20 minutes since I ended my previous class, and it's not done yet converting that. And then after that, I have to load it up to YouTube, which yesterday for some reason took a long time. And while I was waiting for it to finish doing that, I ended up going out to school. And I have to go out to school again today. So I may not get this posted until, I don't know, maybe after 1 o'clock, I'm not sure, something like that. But I try to get them posted. Of course, you guys are already watching it, so that's just the way that it happens to work. I'm going to change our view here over to the IPVO and do a couple more projectile motion problems today. I think we've done about everything you can possibly do with them, almost. And then tomorrow I'm going to look at addition of velocities, and it's kind of an interesting problem where when you have, like, say you're on a moving platform and then you walk on that moving platform, your velocity relative to the platform is added to the velocity of the platform, like if you're walking in a railroad car or something, and that ends up being your total velocity relative to the earth. And I guess then you could add in the velocity of the place you are on the earth relative to the sun, and add the velocity of the sun relative to the center of the Milky Way galaxy, and just keep going forever. But let's not get that detailed. I'm just going to switch over here and do another problem. This is one where we know where the golf ball lands. We know its initial velocity, or no, we know the angle that it took off at, but we don't know what the initial speed happened to be. We know half of the initial velocity, which is the direction. It said it was launched at an angle of 42.5 degrees above the horizontal, but the other part of the velocity, the speed, we don't know. And so let's see what we can do to figure this thing out. Now, it lands at the same elevation, and so that's a crucial bit of information for this that we've used. Now, we recognize that this is a projectile motion problem, so I'm going to see if I can just write down all of these equations from memory. If I start with the x equation, I can just say x is equal to x naught plus v naught x times t. And so I have that thing. Let's see, and v sub x is equal to constant. It's v naught x, which is v naught cosine of theta, or just plain v naught is equal to the initial speed, and then theta is that angle that it was launched at, the 42.5 degrees. So I have that. So there's my x equations. My y equations, a little more complicated. Y equals y naught plus v naught yt minus 1/2 gt squared. Hopefully you're almost at the point where you might have these things memorized. And v sub y equals v naught y minus gt. And finally, v naught y is equal to v naught sine of theta. So got all those things mixed together. Now, here's what's going to happen in this situation. We have some initial velocity, v naught, and this is the angle theta that it makes with the horizontal. The golf ball takes off from there and is going to come down at some point here, and we know how far that is. This happens to be 217 meters. Okay, but there might be a whole bunch of different ways that a golf ball could reach that 217 meters. You could imagine many different arcs for the thing, a shallow arc, a high arc, lots of different things. We happen to know the angle that it takes off at, but somehow we have to stitch these things together and figure out just how it's going to get there. And so I need to somehow come up with an equation where I know everything in it except v naught. And we actually had such an equation yesterday, but I'm going to go ahead and derive it. First of all, I'm going to get an expression for my time of flight. It's just going to be in terms of letters, but the fact that it lands at the same height that it starts from means that over here, its height is going to be y naught again. And actually, I can let y naught equal 0. Okay. That just says that the y position of this entire horizontal driving range is going to be 0. And this is a horizontal driving range. I guess they aren't always that way. Sometimes they've got hills in them and stuff like that, but we've got that. When y again is equal to 0, I can say that my y equation here, y naught plus v naught yt minus 1/2 gt squared, that's going to be 0 again, and y naught is 0. So this simplifies to v naught yt minus 1/2 gt squared is equal to 0. Now, when is this equation true? Well, the way to do it, the variable that we have, v naught y is just going to be a number. G is just a number. At some point, it's t that's the variable. We can figure out the values of t that will make this true. And you do this by factoring it like you did in algebra classes. So what we get is t times v naught y minus 1/2 g times t is equal to 0. So the possibilities that come out of here are that either t is equal to 0, okay, when you have two things multiplied together giving you 0, if those are variable things, then either this one's 0 or this one's 0. And I keep trying to stress that. Or v naught y minus 1/2 gt is equal to 0. And yesterday we solved this equation. The t equals 0 makes perfect sense. This equation is true where y is going to equal 0 when it was launched, okay? And that was t equals 0. This one will tell us the time of flight of this thing. And so the time of flight, kick that across. V naught y is equal to 1/2 gt. And I'm going to do two algebra steps at once here. I'm going to multiply both sides by 2 and divide by g. And I'll end up with the time of flight is 2 v naught y divided by g. Okay, so that's how long it's in the air. And we had that expression from yesterday. This is true anytime a projectile begins and ends at the same height. So I had to go through a little bit of work to get that, but now I know it. Now, I can use this time in my x expression here to figure out how far it goes. And I know how far it goes. That's 217 meters. So I could take this equation x and write it as x minus x naught is equal to v naught x times t. Now I could say that x, excuse me, it's my seasonal allergies again. Anyway, I could say that x naught is equal to 0, or if it's not 0, x minus x naught is how far it goes. This is the 217 meters. And this might be called the range of the projectile, in fact. But if I just take this v naught x and plug this in for t, that will equal 217 meters. And this will be 2 v naught y over g. And so I've got that. What else can I do with this? I'm going to stick in the numbers. Well, actually, I'll simplify that right side a little bit more. V naught x is v naught cosine theta. V naught y is v naught sine theta. And between the two of them, I will get v naught cos theta times 2 times v naught sine theta divided by g is equal to that x minus x naught, which ends up being the range of the projectile. Okay, I'm running out of room. Nothing new there. I really missed I had a computer pad out at school. It was, well, a tablet kind of thing that I could write on. And anytime I needed more room, I just clicked a button at the bottom and I got all this more room to work on. But here's what I can get if I combine stuff in here. I'll have x minus x naught is going to equal 2 v naught squared cos theta sine theta divided by g. Now the x minus x naught for this golf ball is 217 meters. 2 is just a number. G is just a number. Theta is 42.5 degrees. I know everything in this equation except v naught. And if I solve first for v naught squared, I will get x minus x naught times g. And I'll be dividing by, this is doing a few algebra steps at once, but try working through it on your own to convince yourself of this. 2 cosine theta sine theta. Now I know some of you have had pre-calculus 2 or math 142 or trigonometry before and might remember what this happens to be. We can just calculate it, plug it into the calculator, but this happens to be the sine of 2 times theta, if you happen to remember that particular trig identity. Not that it's expected of you. But let's go ahead and plug in the numbers. Actually, let's take the square root first. V naught will equal the square root of all that stuff. And now I'm going to stick the numbers in. X minus x naught, 217 meters. G is 9.81 meters per second squared. Those are the only things that have units in here. And so between the two of them, meters times meters per second squared is meters squared per second squared. But when you take the square root of that, you get meters per second. So that's a reasonable velocity. And then I'll have 2 times the cosine of 42.5 degrees times the sine of 42.5 degrees. All right, complicated calculation, but a calculator can do that just fine. And first thing I'm going to do is hit my square root button, and everything's going to go under that. So 217 times 9.81 divided by, and it's still under the square root, but I'm going to have to wrap this denominator in parentheses. So it'll be left parenthesis and then 2 times cosine of 42.5, and I need to finish off that cosine. And then I probably don't have to put a times symbol here, but I'm going to anyway. Times sine of 42.5. I need one parenthesis to finish off the sine and another one to finish off the denominator. And that's a little tricky to figure out. But then I just hit enter. And I'll get an initial velocity of 46, I can keep 3 sig figs, 0.2 degrees. And so, whoops, not degrees, good grief. We already knew the angle. It's meters per second. That's the speed of that golf ball. So the initial velocity would be V naught. If I put an arrow on it, I could write it as 46.2 meters per second at 42.5 degrees above horizontal. And because I have stated the speed and the direction, that's the velocity. So we have everything here we need. Okay, that one was a bit of algebra to get through, but
Mr. Ham, can you move the paper up a little?
Yeah.
Thank you.
Okay. Oh, huh. My camera has moved. There, that might help a little. But all righty. Well, let's throw a wrench into the works here. And the last problem I had on here is more advanced than I want to look at for this class. So I'm going to do a different sort of problem. I'm going to take that problem, and this is one that I actually do in my other class, but it's kind of fun. And I haven't typed this out for you, but the golfer goes to the moon. And manages to hit a golf ball. Whoops. I don't know what I'm writing. A golf ball with the exact velocity Okay, with the exact velocity as on Earth, which is impressive because he would be wearing a spacesuit on the moon. There was an Apollo astronaut who took a golf club and a golf ball to the moon. I would guess he probably took a golf tee with him too to set the golf ball on and hit a golf ball. And it would be kind of fun to do that. Now we're going to have to know the acceleration due to gravity on the moon. And it happens to be close enough for us is 1.61 meters per second squared. It's about 1/6 of what it is on the Earth. So now we have that. Now here's the complication I'm going to throw into here. The ball lands on a boulder that is 13.7 meters high. Okay. And we'll ask a couple of questions here, but first use G is equal to 1.61 meters per second squared, which is about what it is on the moon. And so Now on the moon, there is definitely no air resistance because the moon doesn't have, with an acceleration due to gravity that small, the gravitational force that's on gas molecules is so little that the gas molecules on the moon are able to leave the moon and not come back because their typical speeds are greater than the escape speed from the moon. So, or a speed that they often have is. So that's a little bit different. But let me show you, if you tried to, say, figure out how long the golf ball would be in flight on something like this, well, one of the ways of doing that is to set up your y equation for a projectile. And I'll just go ahead and write it down here. The y equation for a projectile looks like y naught plus v naught y t minus 1/2 gt squared. So that's the equation. We could say y naught is equal to 0, but at the end of the flight, in this case, y is going to equal 13.7 meters. And here's what happens when I put that into an equation. I would have 13.7 meters is going to equal, well, y naught's 0, so that's gone. But I would have v naught y t, and we'll be able to figure out what v naught y happens to be because we can, we'll just draw a picture and get it. We'll have 46.2 meters per second, and we'll make ourselves a little right triangle here. And the upward part, v naught y, is going to equal 46.2 meters per second times the sine of 42.5 degrees. And v naught x here will equal 46.2 meters per second times the cosine of 42.5 degrees. So we can figure those out, and we will do that because we'll need them. But so this is just a number. But then we'll have minus 1/2 times 1.61 meters per second squared times t squared. And this is going to end up being a quadratic equation. In fact, if I bring everything over to the left side, and actually I may as well calculate v naught y while I'm at it, 46.2 times the sine 42.5 is 31.2 meters per second. So that's v naught y on here. Okay. Okay, so I know everything in this equation. Now, if I bring it all over here to the left side, I will have 1/2 times 1.61 meters per second squared times t squared minus, when I take this to the left side, it becomes negative, 31.2 meters per second times t plus 13.7 meters is equal to 0. Okay. This is like ax squared plus, effectively, bx plus c is equal to 0. And you may remember solving these things in an algebra class, although they never give you numbers this ugly in your algebra class. You might remember that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so you'd have to plug this stuff in. And I'd never make students do this on a test. But here's what I might do. I don't make engineering physics students do this on a test because there's just too much time for, well, it takes too much time to set it up and do other stuff. But what I might do instead is ask leading questions that take you through this thing, and you can figure it out without having to do
Mr. Ham, you're muted.
How long have I been muted?
I think it's been a while.
Oh, well, I was writing everything down. Sorry about that. I don't know how that happened unless well, yeah, I have no idea how it happened. But anyway, the lab I was thinking of doing this week, I can't even remember what it was, but I decided instead to do a Projectile Motion Lab. And I went out yesterday and filmed some stuff. And I'll prepare a video for that this afternoon so you can see the experimental setup. And I've got a projectile launcher in the classroom. And for that, I have people work in teams, and I may make you guys a team. I'm not sure. The four of you, because you're showing up here. But anyway, I have you work in teams, and I first launched the projectile horizontally. And so initially it has no Y velocity, but it's from a desk height. And I launch it sideways from there. And from where it lands, you're supposed to figure out how fast it comes out of the projectile launcher. But then once you've demonstrated to me that you know how fast it came out of there, that you were able to figure that out correctly, I give you an angle and I say, all right, if I launch it from that exact same point at an angle of say 28.2 degrees, and actually I'm not positive how precise I can be on the angles on it, tell me where it's going to land. And it's launched from the exact same height with the exact same speed. And so now you've got an angle and you have to figure out where it's going to land. And then you give me that prediction and I'll go out to school and shoot the projectile at that angle and see where it lands. And that'll be the lab for this week, is coming up with a prediction on that. And I have you work in teams, so but I'm not sure. Salomia, you have a sister, or do you? Somebody's got a sister in this class.
No, I don't have any sisters. I have a cousin with the same last name, though. That's in this class.
Oh, okay. Do you have to work with that cousin, or would you prefer to work with somebody else?
I don't mind. I'm free to work with anybody.
Okay. Well, I think Ty and Ben and Jenna and Salomia, you are going to be a team. And so let me write that down. And I'll set up a Zoom meeting site for you where you can go start a Zoom meeting there and talk to each other and figure this stuff out. So, and you'll have to figure out a time when you can do that. But Ben, and I better be careful. Ben Gmail, that's an interesting last name, Ben. And Salomia. Okay, so you're a team. I can't remember how many people I've got in this class, but the other people are going to have to be the other team. All righty, but I'll be posting an announcement on that, and I won't have time to work on the video for it until this afternoon anyway. But that'll be the lab for this week, and I wish we could do it live. It's one that people really enjoy working on there. We all have to wear safety goggles while we're shooting. It shoots about a 1/2 inch ball bearing out of the thing, but it doesn't shoot it particularly fast. But still, it's kind of a neat lab. But I'll be getting going on that, and I'll see you.
Oh, I have like one question.
Okay.
So this week's lab, so the last question where you're trying to find the gravitational constant for Mars, I think it is. Do you know what I'm talking about?
I'm not sure. What
Here,
was it?
oh,
What was last week's lab?
It was the two-dimensional thing. Yeah, the velocity and acceleration lab.
Oh, okay. Oh, all right. You're supposed to find the acceleration due to gravity on Mars. There we go. All right.
Yeah, and hold on.
Assume that you have a cell phone with you. Okay. I'm guessing if you were going to go there, and on every one of your cell phones is a stopwatch, or at least it's an app you can easily get to your cell phone. I've got one on mine, although for some reason I've got an iPhone 8. My wife has an iPhone 12 or something like that, and they don't have the same clock function on the 12 that they did on the 8, so I don't think she has a stopwatch on hers. But just assume you're going to have a stopwatch, and think about how you determined an acceleration on that lab last week, or that one.
Right. The thing that I ran into is trying to find acceleration. You would need the x velocities of something, but
Have it start with an x velocity of or a y velocity of 0. So drop it. Drop something. Because that's what I did on the track, where I let the ball roll down the track. I just let it start from rest, and it was weird. I just cut out for a second, or the Zoom thing did for a second, but I'm back. Anyway, imagine that you have the ball starting from rest, Ben, and or drop a rock, and just think about how you did it in the lab to measure the acceleration of that rolling ball. And in this case, you want to know the acceleration due to gravity. So you're not going to roll something down a hill, but imagine what else you could do. So
and then there's like one more part. So there's the where you're dropping something down a ramp, and then you do it like halfway down it.
right.
But the halfway point isn't actually halfway.
No, it's pretty close though.
Okay.
It was as close as I could get. And let's see. Yeah, but did you calculate those two accelerations?
Yeah, I figured that they would be similar, but one of them was larger than the other, and I thought that was kind of skewed a little bit because you would kind of assume that they would be the same.
It wasn't enough larger that you couldn't be confident they weren't the same, given that the biggest error in this experiment is reaction time.
Okay, yeah, because I ended up with just like a 4% discrepancy between the two, which I think is fine, probably.
Yeah.
Yeah.
Yeah. Yeah, and that's reaction time plays a huge role in this experiment. Although when I increase the slope, then you got a significantly different acceleration, I think. When I put a second 2x4 underneath the ramp.
Yeah.
Yeah, but if it had been, say, more than 10% difference between the two, then something might have been going on. Maybe they would have had different accelerations, but with a 4% difference, you can't really tell. Just wasn't big enough. Anyway, are you okay with that now? How about the reaction time thing? Have you been able to, any of you been able to do that with somebody else to figure out your reaction time?
Yeah, it was. I set up like a ruler next to my desk and had someone drop the thing and then grab it. Yeah, it
Yeah,
worked out pretty well.
that's the idea. There's an old game you play with dollar bills, and you stick your hands at the bottom of the dollar bill and somebody will drop it. And if you try to grab it before they drop it, then you owe them $1. And if you don't do that and you catch the dollar bill before it slips through your fingers, then you get the dollar bill. But if it slips through your fingers, they get to keep it. So it's not that exciting a game. It's kind of dumb, but I have, and actually I don't like to gamble that way anyway, so I haven't played it, but I've watched people play it. So okay, I'll turn you loose here and get this thing posted as soon as I can. It takes a while to process it, but we should be able to go here. And see you tomorrow.